Ammeter. What is ammeter? So this is a galvanometer to which a low resistance, that is shunt, will be connected in parallel combination. This is a galvanometer. Maximum permissible current flowing through this galvanometer is Ig, and a low resistance that is S or shunt is connected in parallel combination with this galvanometer. We can denote the two terminals of the galvanometer G, and that two terminals are A and B. Two terminals of the galvanometer is A and B, and also these two terminals, low resistance, that is shunt S, is connected. And a strong current or main current I is flowing, and it will be divided into two parts, Is and Ig. Is is the current which will be flowing through the low resistance or shunt S, and Ig is the maximum permissible current which will flow through the galvanometer G. And at the point B we get the same main current, that is I. G is what? G is the resistance of the galvanometer, and S is the shunt or low resistance which is connected in parallel combination or parallel with the galvanometer. And this is an instrument which is known as ammeter, and which measures the magnitude of current in ampere. An ammeter is an instrument or is a low resistance. An ammeter is a low resistance galvanometer. An ammeter is a low resistance galvanometer which is used to measure the current in a circuit. Let S be the shunt. S be the shunt that is low resistance. S be the shunt that is low resistance which is connected in parallel. To a galvanometer, of resistance. Galvanometer of resistance capital G. I is the main current. That is the range of the ammeter. And a major portion of this current, I, passes through the low resistance, that is through the shunt. A major portion of the current passes through the shunt, and that is through the low resistance S, and a small portion under bracket Ig of this current, passes through the galvanometer of resistance capital G, under bracket capital G. Thus this galvanometer does not get damaged. Due to flow of strong current under bracket I through the ammeter, because major portion of current and which is Is, which will flow through the low resistance or the shunt S. As the shunt S is connected in parallel, with the galvanometer G, of resistance G, potential difference across the branch A is B containing the shunt S will be equal to the potential difference across the another branch AGB containing the galvanometer of resistance G. containing the galvanometer of resistance G. So I is the main current or range of the ammeter, and major portion of the current that is Is flows through the low resistance or flows through the shunt. Major portion of the current that is Is flows through the shunt S, and remaining portion of the current, remaining portion is Ig. Remaining portion that is Ig flows through the galvanometer G, so that galvanometer does not get damaged. The galvanometer does not get damaged. In this way, the galvanometer is being protected from the strong current I. And here potential difference across the branch ASB will be equal to the potential difference across the branch AGB containing the galvanometer G. S is the shunt, and which is connected in parallel combination with the galvanometer G. And here potential difference across this branch ASB is VSB, and potential difference across the branch AGB containing the galvanometer G is VAGB. So in the equation what we can write in the given relation, what we can write, VSB equal VAGB, VSB equal VAGB, or comma Is dot S, product of current and resistance, is equal to Ig into G, or comma S equal Ig by Is into G, S equal Ig by Is into G, or comma S equal Ig divided by I minus Ig, bracket closed, into G, where the main current I is equal to sum of Is and Ig, where the main current I equal Is plus Ig, is equal Is plus Ig. And we get the expression in here, Is is the current which is flowing through shunt, and Ig is the current which will be flowing through the galvanometer. And S equal Ig divided by I minus Ig into G is the shunt, or low resistance which is connected in parallel with the galvanometer. S equal Ig divided by I minus Ig, bracket closed, into capital G, which is the shunt connected in parallel with the galvanometer G. When a low resistance that is shunt, that is a shunt under bracket S, when a low resistance that is a shunt under bracket S equal Ig divided by I minus Ig into G is connected in parallel with the galvanometer of resistance G, with a galvanometer of resistance capital G, comma, it will be converted into, that means the galvanometer will be converted into an ammeter, of range, 0 to I, an ammeter of range 0 to I, that is of range under bracket 0 to I, that is of range under bracket 0 to I. In general, the current flowing through galvanometer, that is Ig, is measured in milliampere, MA. Ig is measured in milliampere unit, and I will be measured. I is measured in ampere unit. That means Ig is very small current, and I is much greater than Ig. I is also known as the range of. I is also known as the extreme value of the range of the ammeter. I is also known as the extreme value of range under bracket 0 to I of the ammeter. Now S is equal Ig divided by I minus Ig into capital G. That is the required shunt which is to be connected in parallel with the galvanometer, or comma I minus Ig divided by Ig into is equal G by S, or comma I minus Ig minus 1 equal G by S, or comma I by Ig equal 1 plus G by S, and I is equal to S plus G divided by S into Ig. I equal to S plus G divided by S into Ig, which is the extreme value of range of ammeter, which is the extreme value of range under bracket 0 to I bracket close of the ammeter. That means I is the range of an ammeter. I is the range of an ammeter. Hence, if the value of shunt under bracket S is lowered, comma, the range of the ammeter, the range under bracket I of the ammeter will increase. So in the expression if the value of shunt is lowered, if the value of shunt S is lowered, comma, the range, that is capital I, will increase, not increased, it should be will increase. So here the effective resistance of the ammeter is Ra equal G into S divided by G plus S, because shunt S is connected in parallel with the galvanometer of resistance G. That's why the effective resistance of the galvanometer of the ammeter will be what? Ra equal G dot S divided by G plus S. G dot S divided by G plus S. Therefore, 1 by Ra equal 1 by G plus 1 by S. Therefore, 1 by Ra greater than 1 by G. Therefore, Ra less than capital G. So, the effective resistance of the ammeter, is less than that of the galvanometer. Another theory regarding ammeter, we can consider the effective resistance Ra, which is equal to G dot S divided by G plus S. Now let the shunt S be very small resistance, therefore S is approximately equal to 0. Therefore Ra is equal to G into 0 divided by G plus 0. Therefore Ra equal 0. Thus we can say that the effective resistance of an ideal ammeter is 0. The effective resistance of an ideal ammeter is 0. And also you can say that for an ideal ammeter, the shunt should be very small. For an ideal ammeter, the shunt S should be very small, and the effective resistance Ra is also 0. In the diagram, we have a galvanometer of resistance G, and Ig is the maximum permissible current for the galvanometer G, so that galvanometer does not get damaged. And let G be the resistance of a galvanometer. Ig is the maximum permissible current, maximum permissible current flowing through the galvanometer, of resistance G, and Ig is also known as the extreme value of the range of current. Obviously, Ig is also known as the initial extreme value of range of current under bracket 0 to Ig, which the galvanometer can measure. Now we can consider that a shunt or low resistance is connected in parallel with the galvanometer, and Ig is the current which will be flowing through the galvanometer, and Is is the current which will flow through the low resistance or shunt. To increase the range of this instrument, from 0 to Ig to 0 to I, a low resistance, that is a shunt under bracket S, is connected in parallel with the galvanometer of resistance G, such that major portion of the main current I, flows through the low resistance shunt as Is flows through the low resistance, that is through the shunt S, as Is, and the remaining portion of this current, and remaining portion that is Ig of the main current I flows through the galvanometer G, so that the coil of galvanometer does not get damaged. Now S is equal to Ig divided by I minus Ig, bracket closed, into capital G. That is the expression of a required shunt which will be connected in parallel combination with the galvanometer G. So S is equal to Ig divided by I minus Ig into capital G. That is the shunt. Let I equal Nig. That means the main current I is n times of the maximum permissible current Ig. So here Ig is the initial range of galvanometer. And I is the final range of the ammeter. And we have to increase this range from Ig to I, so that I equal n times of Ig. Therefore, S is equal to Ig divided by Nig minus Ig, bracket closed, into capital G, equal Ig divided by Ig, bracket open, n minus 1 into capital G. So finally we get S as G divided by n minus 1. S equal G divided by n minus 1. That is, the required shunt S is equal the resistance of galvanometer divided by n minus 1. S is equal G divided by n minus 1. This is the required value of shunt. This is the value of shunt resistance. To be connected in parallel with the galvanometer of resistance G. This is the value of shunt resistance to be connected in parallel to the galvanometer of resistance G. In order to increase the range of ammeter, by n times, This is the value of shunt resistance to be connected in parallel to the galvanometer. Value of shunt resistance to be connected parallel to the galvanometer G in order to increase the range of ammeter n times. In order to increase the range of ammeter n times. Now, if we want to increase Ig to I equal n times of Ig, then the value of shunt S will be G divided by n minus 1.